So good morning, good afternoon, good evening to all of you. Welcome to the KiboCUBE Academy online live session. And thank you all for participating. So KiboCUBE Academy is an educational series that UNOOSA, United Nations Office for Outer Space Affairs, JAXA, Japan Aerospace Exploration Agency, with the support of the UNISEC, University Space Engineering Consortiums, to provide theoretical knowledge to develop, operate, and utilize small satellite. So for the people who enter this meeting as panelists, please leave this webinar once, and then join from the correct URL. So thank you for your participation. So okay. Before we begin, I want to explain a few administrative announcements. So first of all, if you have any questions, please use the Q&A box to ask them. So you can click the Q&A icon in the toolbar and type your question and then click. So your questions in the Q&A box will only be delivered to the host and the panelist. And we want the questions and answers to be open to all of you. So please make sure to write your questions in the Q&A box, not in the chat. And when you write your questions, please state your name and affiliation. Second, please answer our questionnaire or your feedback that we will be putting in the chat box later on. And we will also sending you the URL after this webinar. So we would like to hear your feedback on the KiboCUBE Academy. So please make sure to answer that so that we can improve our future sessions. Third, if you are active on SNS, please use the hashtag access to space for all, KiboCUBE or KiboCUBE Academy, and follow, like, and state UNOOSA and JAXA to help us promote our activity. So today's agenda looks like this. So first, we like to take this opportunity to give you an overview of the KiboCUBE program, which is currently open for applications until the end of this year. After that, the main focus of today's webinar, we'll be doing the lectures of lessons learned of CubeSat missions delivered by Dr. Mengu and the Q&A session. Then I'd like to briefly introduce a KiboCUBE program. So KiboCUBE program was established in 2015 in partnership with Japan Aerospace Exploration Agency, JAXA. And currently, 9th round is open for applications until the end of this year. With this program, we will provide educational and research institutions from developing countries with the opportunity to develop a CubeSat and deploy it from the Japanese experiment module Kibo of the International Space Stations. So this slide introduces past awardees of the KiboCUBE program, and you can see, as you can see, we have selected awardees from Africa, Central and Latin America, and the Asia Pacific countries. So far, 5 CubeSat from Kenya, Guatemala, Mauritius, Maldives, and Indonesia have been launched, and out of 5, 4 satellites have been the first of each nation. And the CubeSat from Mexico has been launched to the ISS and ready for development early next year. And CubeSat from the Central American Integration System SICA and the joint team of Tanzania and Cote d'Ivoire are currently under development. So in the 9th round, we are planning to select one or a few applications depending on the content of the applications. So if you are interested, don't forget to submit your application by the end of this year. The selected team will receive technical assistance from our partner organization JAXA from development to launch and deployment. how to apply all the documents, including application document, reference materials, frequently asked questions and their answers are all uploaded on our website. So please carefully review all the documents and submit all required documents to us by the end of the year. Regarding to the eligibility, this program is only to government organizations, research institutes, universities, and other public organizations located in developing economy and economy in transition that are member states of the United Nations. For the definition of the developing economy and economies in transition, please check our report, World Economic and Situation Prospect. Therefore, the entity in developed country and private company even in developing country are not eligible for this program. KiboCUBE Academy. So finally, this KiboCUBE Academy, including today's webinar, is one of the educational contents to support current and potential KiboCUBE awardees and anyone interested in developing CubeSat. In cooperation with JAXA and the support of UNISEC, it covers the fundamentals of designing, manufacturing, testing, operating, and utilizing a CubeSat. So today we cover the topic of lessons learned of CubeSat missions, but if you are interested in more about CubeSat, there are 27 on-demand pre-recorded lectures on our website. You can see the topics on this slide, and you can access presentation and videos online at any time. Okay, so this concludes my presentation. And next, I'd like to introduce Mr. Takuya Ozawa from JAXA, and he's going to explain in more details about the process and the flow of the selected CubeSat for the KiboCUBE program. So Ozawa-san, you have the floor.
Sure. Hello, everyone. Thank you for joining this conversation meeting. I'm pretty happy to have so many people here. And now I'm going to share my screen. Yep. I think now it's working. Yep, so I'd like to explain about some basics about a KiboCUBE satellite and also the deployer, which is called JSOD. So first of all, I'd like to explain about Kibo, Japanese experimental module. So this is the ISS, as you may know, and this is the part circled with this one is called Kibo, which is Japanese experimental module. So this is like Japan in the ISS. We can make use of it freely, kind of freely. And JSOD is something like this. So here, this is the tip of this arm here, and this is, the Kibo. So Kibo has an arm, just like our arm here, and this arm can catch kind of anything. And your satellite deployer is held by this arm, and then your satellite is inside here, and then pushed by spring force to space. This is the basic of the JSOD, and now I'm going to explain about how your satellite development will go after you are approved through KiboCUBE program. First, actually, you can work with JAXA. Actually, I'll be working with you if you're approved. One of the support we are going to provide is that bi-weekly or more, we will be having a meeting to discuss component procurement or safety review, development status, almost anything else. As you can see, this is about 100 people, and this is me. And also not only the online meetings, we actually visit your country probably once, hopefully more. And this is the pictures when we visited Mexico about about 1 year ago. We actually here, we are discussing about some testing procedures or assembly procedures, which is pretty important for your satellite to make sure that your testing requirements meet our requirements, NASA or JAXA's testing requirements. And also we actually check your satellite, your flight model. And this is one of the pictures we took there. And like after this development process, you will bring your satellite to Japan JAXA. And after you brought it, we will be doing the final check just like this. And then after you passed it, hopefully passed it, so we will take some pictures. So Samara-san is here and I'm here and they are happy. This is one of the happy moments we can have. And after that moment, we will install your satellite into the case. So this one is like your satellite, and we will put your satellite into this case. And we will be covering it with these cushion pieces, just like here. So this inside of it, this is the case, and we cover it with these cushion pieces. And then we will cover it with some kind of anti-static, anti-electric static. Oh, anyway, and that kind of sheet. And then we will transport it into the launch site. Sometimes it's Japan, sometimes it's the States, United States. And then we will launch it to the ISS. So hope your baggage something around, I think, around the tip. And then after the rocket reaches the ISS, an astronaut will unpack it just like this. So as you see, so this blue one is just like now he's holding it, he's unpacking it. And then after he unpack it, he puts it into the platform. This platform is something which can be held by the arm I introduced earlier. How it works is like, obviously this is like the door. And in the next page, this is what we call, I forgot the door, airlock. Yeah, airlock is this. So like this can be, this can slide into the outside. So like after he put it into the platform comes out from this airlock, and then the arm can catch it around here. I'm going to finish in a few minutes. And then this is something like after when the satellite is ready, the picture of just ready, and then just before it is launched. As you can see, this here, we have a door, and then a door is holding the satellite here, and then we open it, the satellite naturally comes out from the case, thanks to spring force. And then everyone is happy, like they are, sorry for that. Everyone is happy, they are developers, the satellite teams here. But after, of course, like the main part is after your satellites deployed, you have to operate them. It's about your missions, and that is one of the most important parts of the satellite development. And about that, Dr. Mengu will make speech about this one, about missions. So I hope to work with you in the future, and then we can have this kind of moment together. Yeah, that's all from me. Thank you.
Thank you, Ozawa-san. And wait a minute. Okay, let's let's move. Before we move on to the lecture, I'd like to make two announcements. So first, if you have any questions, please use the Q&A box to ask them. You can click the Q&A icon in the toolbar and type your question and click send. And when you write your questions, please state your name and affiliation. And the second announcement is today's presentation and the recording will be uploaded our website later. Okay, so let's move on to the session now, today's main part. So I'd like to invite Dr. Mengu Cho, Kyushu Institute of Technology, and UNISEC on lessons learned of CubeSat missions. As you may know, Dr. Cho is an expert who has been involved in CubeSat development and education for many years. So we look forward to hearing very interesting story and lessons learned from him based on his valuable experience. So I turn it over to Dr. Cho. So you have the floor.
Okay, thank you. Thank you very much, Sasuma-san, for the introductions. Now, I'd like to make presentations. Yes. Okay. So, lesson learned. So this is my brief background. Yes, and yes, I have been involved in these the number of CubeSat and satellite for the more than 10 years, and I just counted those number of projects. It's now number 19. Yes, and this satellite is now orbiting, and this satellite is now orbiting. This will be released very soon, and we have another other satellite in the pipeline. Okay, now okay. For today's lectures, first introductions. So I'll talk as a member of UNISEC Japan today. UNISEC Japan is called University Space Engineering Consortium. It is a non-profit organization, consists of many universities and professors and students. Yes. So we maintain this cooperative relationship, and we conduct practical space development and utilizations. And so this is some examples of CubeSat and satellite launched by the UNISEC members. I think these we show satellite only up to 2020. So I think we have more than this. And during the pandemic in 2020, we had a lot of free time. So we utilized time to something meaningful. And we did these remote sessions on lessons learned because we had many times. And during that time, each professor or PIs talked about their project, about 3 hours per project, very honestly, what really went wrong, what was really successful, and we really showed everything. And that activities got attention of JAXA, and they said it's a very good activities. They want to support that one. So, so the sponsored by JAXA, we made this very big report about analysis about success and failure case of the micro nano satellite, and we try to extract the requirements for mission assurance for the micro nano satellite. And these activities continued. It continued until even now. Yes, and so we've been working on the mission assurance. And in 2021, we published this mission assurance handbook for university-based green satellite. So we did a further analysis of failure cause by intensive interviews with the persons in charge of the project. And based on that one, we published this handbook. And this lecture will provide some examples of lessons learned and failure root cause and how to improve the mission success rate through this activity. So lessons learned and root cause. So this is the major point of today's lecture. And so we did a lot of interview. And we selected some project which failed. It was very painful interview for the PI, but each PI really helped because we all wanted to have a mission success rate improved. So this is one example, 3U CubeSat. Satellite was very difficult to assemble. Every time when satellite was assembled due to testings, it suppressed the schedule significantly. Part of the reasons was that during the safety reviews, the team promised to do 3D measurement each time the satellite is assembled. Because they are big university, and next to their laboratory, there are some places where they have very expensive 3D measurement machines. So perhaps they wanted to prove that they can do that kind of thing. However, setting up those machines and measuring and those things took 1 day or more each time. So that suppressed schedule significantly. Because of that one, software development progress was far behind hardware development. And so they didn't have enough time to do all the software testing. And in the orbit, eventually, due to the collision of I2C, satellite entered a mode of infinite loops of resetting. Eventually, satellite recovered after more than a year. However, yes, they had to wait for that one. And the root cause was that why it took so much time for each time they assembled, or because they promised more than enough for safety requirement verifications. Safety requirement verifications is a necessary activities, but it's not value-adding activities. So you try to finish that activities in a minimum time, minimum shortest possible time, and use the time saved to a more value-added activities to improve the mission success. So 3D measurement was not really necessary. You can use simple measures to measure the size of a satellite. Also, in a project, especially in the mission definition phase, only faculty members were involved. And students were asked to join the project after the mission was defined. So it wasn't good to encourage student motivation. And schedule management was poor because it was their first satellite. So they underestimated this long-term end-to-end test. And so that time spent in this end-to-end long-term test was not sufficient. That's why they had the issue in the orbit. And also satellite structure was too complicated. They're from mechanical engineering department, so they want to make something very mechanical. But they didn't have experience in the satellite design, so they didn't have a proper level of the satellite. Yes. Perhaps they are too detailed and too meticulous or something. Yeah. Case 2, one CubeSat. This one is a really so-called dead-on arrivals. It was released from the, I think it was from the, I think it was from the rocket, yes. It was released from rocket, but no signals was received by the ground station. Yes, nothing. And there were many single point of failures in the satellite design. So the team did lots of intensive fault tree analysis. They tried to identify what went wrong. There was a strong possibilities of connecting solar cells in a long way. This is a satellite solar cells they use. This is so-called integrated bypass diode functions. This is the bypass diode. It looks like these are electrode, N electrode for the solar cells, but actually no. But a student may have mistaken as the this N-type electrode. So they connected in a wrong way. So that was a very strong candidate. And the delivery date was fixed. It was a free launch by JAXA, so they have to deliver the satellite by the deadline. Otherwise, they miss a bus. Yes. So they have to catch a bus to go to space. And so the satellite had to be delivered regardless of its condition. So it really stressed the schedule. So it was the first satellite. So they don't know what to do to build a satellite. And above all, they didn't know where to ask, even if there is a question. They could ask some expert about this one, and expert easily identify, and they can say that, yes, don't make a mistake, this diode, and connect in this way. So it was a very simple advice. But they couldn't even get that one because they didn't know even where to ask a question. And another one, case 3, 2U CubeSat. In this case, ground station preparation was insufficient. Checking its functionality means the ground station functionality was not done using other satellite in orbit. So even if the satellite was launched, actually ground station was not really ready. The reason was that the university team was from mechanical engineering department. Usually, if you are from mechanical engineering, you don't take any course about communication, telecommunication, or even radio, or you may take some course about electromagnetics, but it's not enough for the radio communication. So the team depended on external supports regarding communication system, but it was very difficult to point out problems by the system test done at the university because the team itself didn't have enough expertise about how to test, what to test in a communication. So they depended on the amateur radio expert outside campus for the radio, but the communication between the expert and the student was difficult due to physical distance. I think they were about 150 kilometers separated. So the principal faculties couldn't take care of those gaps properly. And also, yes, they didn't have enough expertise for the satellite project. They are very strong in the mechanical design, but not in communication. Case 4, it's not a CubeSat, but it's 50 kilograms Earth observation satellite. And in this case, satellite power budget didn't have enough margin. And because of power shortage, very frequent satellite reset occurred. So the setting was if the battery goes down certain levels, satellite reset. So reset was okay, and the satellite could reboot every time. But every time satellite rebooted, attitude control history, it was overwritten. And very complex attitude controls had to be restarted once again. So they have to upload all kinds of the settings about attitude controls. They have to tune the gains and their values of all the sensors, and they have to uplink many commands. And it took so much time to establish proper attitude for the mission. So the mission was camera captures and high-speed downlink. And for high-speed downlink, they needed to have attitude controls because the beam is very narrow. For UHF, it's okay. UHF, no matter what your attitude was, you can communicate. But for, I think this one uses KU band, and the beam is very narrow. So if you miss ground station, you can't communicate. And so because of insufficient attitude controls, no image data could be downlinked. So the mission failed. Again, it was the first satellite for the team. I think many of our audience today, if we are trying to apply for the KiboCUBE, it's the first satellite for you. So all of these kind of lessons may more or less apply. For lack of experience in the satellite system design, development, operations. And no time to the full system test to check the power budget and the flight representative conditions. So couldn't do test as you fly. So important word in the testing is the test as you fly. So you test the satellite as if it is really flying. So you do not attach cables because in space, satellite doesn't fly with cables. All the communication is through the radio. Okay. You check the satellite telemetry and you understand how satellite conditions. It's not by the details or debugging cables connected. Yes. For this one, this history of attitude control, I think it's very important. Actually, our satellite at the QTech, we had the same issues. It wasn't our first satellite, but it was our first satellite to the free axis attitude controls. And we underestimated these all the steps to uplink those attitude controls parameters. So we had the same issues. Yes. So it was also very difficult. Yeah. For case 5, another 50 kilograms Earth observation satellite. And in this case, battery was not designed to stop charging once it's fully charged. I think it's a very bad design, yes. And it forced very delicate charging maneuver in orbit. So they need very the delicate tuning. And also in a power system design, this is a solar cells. Bypass diode is the diode to bypass through this solar cells when some of solar cell in shadow. Blocking diode is to protect if some short circuit occurs, if some anomaly occurs, this current generated by these solar cells will not go this way, will go this way. So without this blocking diode, if this string is lost and short circuit, power from here may go this way. But they had no bypass diode or no blocking diode in solar cell circuit. Apparently, the team didn't know about this importance of bypass diode and blocking diode. And the shadow on solar panel circuit killed entire solar array circuit on 50 centimeter panels. And when the voltage became low, the satellite computer became a kind of zombie state. And because they needed a very delicate this maneuvers in the battery condition, so it couldn't recover fully. And so it cannot function, no, it cannot be rebooted. So it's really zombie state. So again, it was the first satellite of the team. and the lack of experience to check design made by the EPS contractor. So they knew that they were weak for the EPS system design. So they asked the subcontractors to design entire EPS systems. And EPS contractors, they claim to make EPS systems for a big satellite. But because they were not told about this charging controls, they didn't implement that one. And because the system side didn't put in the specifications, and the contractor didn't do anything. So system side should have known the specifications at least, not how to design, but they should specify all of those things. So also, they didn't have experience in a system test, and so because of the this recovery from the reboot, they couldn't test properly. K6 7 kilograms education tech demo satellite. Actually, this is my first satellite, Holly 2, which was launched 2012. Yes. Our satellite deployment was successful, and housekeeping data was collected for initial 3 weeks from the deployment before doing the mission. So first initial 3 weeks was perfect. It was working perfectly. But the communications with the satellite was suddenly lost due to single event latch-up. Yes. We are talking that well, we should start the missions soon. We should stop collecting all the housekeeping data because we are new to this area, so we are really excited having even housekeeping data. So we are wait but we forgot to do the missions. Yes, and also we are kind of overconfident. That one, yeah. And well, satellite recovered due to power reset, but operation time was limited. Operation time was limited due to a series of disruptions caused by SL. This single event latch-up occurred many times. Well, this is the latch-up current. Once a latch-up occurs, current jumps up to about more than 200 milliampere. And this is the data which we captured during the recovery. It is very rare data. But anyway, we could capture this one. And satellite recovered and went back to normal state. Yes, this is a 50 milliamperes normal state. This clearly shows latch-up occurred. And we should have the overcurrent protectors, which is kind of a circuit breaker. By monitoring this kind of current, and once the current exceeds certain threshold, we should do power reset intentionally. But this overcurrent protection, it didn't work. We had that one. We had that one installed, but didn't work because we set the threshold values to 500 milliampere. Actual latch-up current was, yes, you can see from this one, 200 milliampere. So the threshold was around somewhere around here. So it never worked. For the root cause, we decided this OCP threshold without any basis. So I asked the student later why we chose 500 milliampere. And the student said, I was talking with JAXA persons, and I said 500 milliamperes. And JAXA person said, well, probably it will work. And so we thought maybe it will work. Yes. So no basis on that number. So SEL protection was designed, but not verified. And also, initial 3 weeks, we actually wasted by just collecting housekeeping data. Well, not wasting, but we should have done the main mission much earlier. Yes. So that was a hard lesson. Now I tell the every satellite project, do the main mission on the first day if possible. So satellite may die anytime. It's not only our satellite, many other satellites, yes, have this kind of issues. Yes, initial 1 week is really critical. Initial 1 week, many satellites dies. Then you should do some missions in initial 1 week, yes, so that you can achieve at least kind of minimum success criteria. Okay, case 7. This is another our satellite also. This is the buzz 1. Yes. We use this experimental patch antenna, this one, for both UHF and VHF. This patch antenna I liked. I like this patch antenna because we don't have to deploy the antenna. Antenna deployment, UHF, VHF deployment is really critical. If we fail to deploy the antenna, we cannot communicate. We actually had that kind of issues in other satellite too. So by having this patch antenna, no deployment, so it's very reliable. And I had a colleague and who was an antenna specialist, and he said that okay, I can design antenna for you. And we actually wrote a paper for that one. Yes. And however, the gain of this patch antenna, I think for the engineering model was good, but for the flight model was not good because because of this one, we could hear the downlink, but no uplink. So we had 5 satellites, all the same design, and all of 5 use experimentals this patch antenna. And so we couldn't communicate with all of 5. Well, we could hear the beacon from all of 5, but no uplink to all of 5. And this problem was not detected by ground test because flight model antenna, this arrived at the last minute, and we didn't do no system communication test. So that was very hard lessons. Yes. So EM was okay, but FM was not. So, and the biggest lessons was that satellite designs, it involved this design, a demonstration of new technologies. But the main mission was education. So it was very inconsistent. Actually, I tried to chase 2 rabbits simultaneously, but both rabbits are gone. Or try to catch 2 birds by 1 stone, but the stone missed the 2 birds. And also lack of expertise in communications. I'm not a communication specialist, so I couldn't understand the risk of a patch antenna. So by just looking at this one, risk of deployment failures is avoided, so I just jumped. And should have considered advantage of constellations more. So I should have selected strategy of making at least 1 satellite survive than making all the satellites survive. So if we put the experimental technologies, because I had 5, I should put only 1 satellite. I should attach this patch antenna. Other 4, I could have the deployment antenna because I had a 4 satellite, maybe 1 satellite succeed in deployment. So the use of patch antenna was made only by the principal faculty, it's me. No other member could challenge the decision. It's very bad. Yes, very bad. Yeah. So I should have listened to others. Yes. Case 8, this is about 2. Yes, this is about 2 satellite. So after learning these lessons, But we use this the deployable antenna, and the UHF beacon was improved drastically. Yes, but we still had the uplink difficulties, and it was we later found it was due to internal noise generated by the EPS board. Yes. Because of the lessons we learned from the previous project, we did this system test. So we tested FM in anechoic chambers and put the this antenna, and but we couldn't detect because during the ground test, internal attenuate of 10 dB was in the reference dipole antenna. It was overlooked. So we overestimated 10 dB in the link budget. That's why we couldn't. It worked on the ground, but in space it didn't work. So we couldn't manage this 10 dB deficit. So the root cause was that few expertise in the communications couldn't check the test setup consistently. Well, we had one student who was very good at communication. And for that student took care of all of the communication tests. So we relied too much on him. And he overlooked this 10 dB internal attenuator. So that's why. We shouldn't blame him, but we should blame all the management structure. And also, we had no knowledge that internal noise affect uplink signal reception. So we later found, sorry. We later found uplink was difficult because of internal noise. It was affecting uplink signal. So in a link budget, we chose background noise, but that value was chosen without any basis. So we should actually calculate link budget based on testing using flight model. That's a really important lesson. So these are the example of the lessons. So based on those lessons, yes, we have based on those lessons, yes, we have made mission assurance handbook. So in the example shown, you could see many common causes among different cases. First one, poor schedule management, especially for the first satellite. Insufficient team talent and skill. I think it's very rare in a university project that you have all the talent. Some talents, communications, or mechanical designs, or software. Some talents are probably missing. So you have to think how to manage those missing talents. Inconsistency in the requirements, improper verification plannings, wrong strategy to avoid total satellite loss, insufficient full system end-to-end test, difficulty in assembly integration testings, and poor understanding for rationale behind the design. I think this is more important for the second satellite, third satellite, or many other things. So let me talk about the mission assurance. So what is the mission assurance? Mission assurance is a series of activities to identify the factors in design, making, operations of the satellite that will jeopardize mission success and to eliminate or decrease effect of such factors. So it's very similar to risk management. You identify risk which may jeopardize your missions. and you try to mitigate those risks. And the university satellite is categorized as a lean satellite. Lean satellite, by definitions, or satellite utilize non-traditional risk-taking development and management approach with the aim to provide satellite value to customers and or the stakeholders at low cost and short time to realize satellite missions. So this covers all of the so-called small satellite, small, nano, pico, micros, CubeSat, everything. Yeah, more or less. So we can also say new space approach or something. For lean satellite tolerate risk, but we still need to achieve the mission success as much as possible. So in a lean satellite, we don't say failure is not option, but we don't say failure is accepted. So we take a risk, but we try to minimize the risk as much as possible. So we made this mission assurance handbook. So we target satellite project at universities and polytechs in Japan. Not only the first project only, but also second and later project. We list a summary of points to be kept in mind of the faculty members and students to improve the mission success rate. And we organize in order of project life cycles. And we publish and available in lines and much of content applicable to satellite project in new space.
Yes, I'm muted.
And non-Japanese organizations. So we have an English version. We have an English version, currently version 4. So you can use smartphones and capture the QR code below. You can directly go to the English version. And if you miss last one, yes, this one, yeah. So the contents is from introductions, project management, mission definitions, conceptual designs, detailed design, production, testing, operation, post-operation. So this is the ordering according to project life cycles. Depending on where you are, I think you can look at it. And last chapter is sustainability of university satellite programs. So it's not long, it's about 50 pages. So you can read in 1 hour or the hour and a half, yes. So now let me explain some of the key points. Yes. First, for the project management, the schedule management is important. For first project, often fails improper schedule management due to lack of satellite project expertise. So it's very little time spent in the system test. And so we have these guidelines for the project milestones until the satellite delivery. This is, I think this is the minimum time you need. So this is a D-13 months, D-13 months. You finish proof of concept. You confirm the missions are feasible and finish EM design and start procurement. This is D-13. Typically, you have PDR, preliminary design review. You don't need to have a hardware, but you know from the simulation analysis, or sometimes you may use something called BBM, breadboard models. So anyway, you finish proof of concept. So at least you know the mission is feasible. Then you start procurement. And procurement takes a time. And you should account at least 3 months for all the EM hardware component comes and ready for system assembly. It takes about 4 months to finish all the EM testing campaigns, confirm that the satellite function as a system. 4 months. Okay. If you are really beginner, it may take even more. These numbers are based on our past experience. And sometimes beginner satellite can do with this time frame. If your satellite bus is well established and a student works very hard. So it is possible. But allocate, I think, at least 4 months or something for the year. And after that one, you have usually critical design level, CDR, critical design level here. After that one, you move to the flight model procurement. So you assemble the flight models, and 2 months hardware and software testings, and ground station software is complete. D-1 month, and for the final 1 month, if you can do the software testing consistently and with the ground stations and know how satellite behave in the orbit. Okay. You cannot fix hardware, but you can fix software. But when you fix software, be careful that by modifying software, another bug may enter. So you really have to be, you really have to be cautious to modify software at this last minute. Okay. And team talent, it's not too possible to have all the talent necessary for the project by student alone. So you need to find a solution to fill the shortage. For either procurement, you buy components from the market. Yes. Collaboration with external peoples, you invite other peoples to the teams, sometimes even from outside the universities. Or you can expect students to grow. If students have infinite capabilities to grow, yes, yes. Sometimes they grow so rapidly, yes, so great. However, it's risky. It's risky. It's risky to rely on the student growth. And so, but even for 1 or 2, requirement for the procured or outsourced item must be made by the team. Because after all the system tests must be done by the team. Yes. Also, it's important to keep the person familiar with the satellite design for operations. Because once a satellite is operated, sometimes it doesn't work, or it doesn't work as designed. So you need a person who really understands satellite. In that case, you need to finish the project life cycles from kickoff to the operation in 3 years. 3 years, many cases in the university student stay. If the students start a project from an undergraduate senior year, if the students move to the graduate schools, usually master course is 2 years, so they have 3 years. Or if you try to finish everything in undergraduate, you start from the end of first year or something, or beginning of second year. So the principal investigators, usually it's a faculty member, is responsible for keeping student motivations and responsible for securing communication channel for the external assistance. So students may need to ask questions to others, may need to go to ask for help, but usually they hesitate because they are told by their supervisors, go to this university B, ask Professor C there, and ask their questions. But the students are very afraid to go to see the professors. And in that case, the principal investigator just make a phone calls to or write an email to the outside professors saying that our students need help. Could you help them? And with CC to the student, then it's very easy for the students to go. So that kind of things necessary. Students are sometimes very shy. Yes. And the safety requirement verifications. For non-compliance with the safety requirement may lead to serious delay of the satellite. Serious delay of the schedules. In the worst case, the satellite is not launched. Dummy mass will go instead of your satellite. Well, this is a very scary picture. It actually happened. This is a 4 piggyback satellites. Actually, this is our satellite, Holy 4, our second satellite. This was supposed to be a bunch of CubeSat, but it failed safety verifications. So instead, they put a dummy mass. So we need to avoid this kind of situation as much as possible. So at the end of conceptual design and the detailed design phase, we list up the issues related to the safety requirement and confirm with the launch providers. And so that no misunderstandings occurs. And I think it's better to do either in person or by video conference, not by email. Yes. In the emails, usually, I think small, minor, very small things are not clear enough. So you may want to clarify everything. And you agree with the launch provider on the safety requirement verification method that can be done with a minimum method. Remember those 3U CubeSat, which promise that to do 3D measurement. It's not necessary. For safety verification is necessary, but non-value adding activity, do more value adding activity such as a mission assurance. So anyway, communications with the launch providers or launch brokers is really important. You need to have a very frequent communication. And feasibilities, you should know the limit when you define the mission, team talent and skills. There are some missions you cannot do, and there are budget, of course. And you should understand professor is not God. Or professor is very good at pretending that yes, I know everything, but usually not. Yes, and so he or she doesn't know everything to judge the mission feasibility. So even if the professor says yes, we can do, or even if the professor says we cannot do, don't trust. Okay, think about yourself. Okay. Also, if you're a professor, you should be open-minded to suggestions, comment, assistance by others, because deciding alone is risky. For example, free axis stabilization from a first satellite, I think I would say no. Yes, it's too complicated for first ones. High-speed communication by mechanical student, I wouldn't recommend that one, because it's too much their expertise. Okay. And in a conceptual design phase, requirement management. So you check the consistency between mission requirement and the design requirement. So design should satisfy the mission requirement. There should be no design requirement that doesn't fit to the mission requirement. Every design requirement must fit to the mission requirement. And for that one, external review by experienced expert is effective. Yes. So external reviewer may say, why you have this patch antenna? I may have said, yes, we can avoid risk of deployment, but the external reviewer may have said, well, patch antenna usually have a long gain or something. Yes. And or I may have think twice. Yes. And open mind to external suggestion. And verification plan. So you have to use design that can be verified. Yes. For radiation mitigation, yes, it's important. Okay. And you should have a doable verification plans. Yes. And this is the list of a minimum test item or ISS related CubeSat. So if you have the KiboCUBE, yes, you should look at this one. Yes. And these testings are end-to-end long-term. It's important. Yes, those things. And risk management, FTA, FMEA. So you try to minimize the risk based on the priority. There are many risks, but you prioritize. Priority risk is a risk which may occur with a high probability, and risk, if it occurs, its damage is so significant. Those risks are really priority. So external review is again, it's effective to list up risk with high priority along with the safety issues. And FTA, FMEA, if you don't know what the FTA, FMEA means, yes, you start from these levels, you can understand. So you start from listing up single point of failure and prioritize the risk. Also, not only the parts component, but also work, like a long command and long assembly, those things. Human makes a mistake. And during testing phase, this electromagnetic compatibility test is important. Well, the EMC with launcher and other satellites are not important because your CubeSat is launched in cold, the power is off. So no way to affect others. So however, you have to live with the self-generated noise. So you verify command link has enough margins, so especially this uplink. Uplink signal levels is much higher than satellite-generated noise force. So you confirm first before moving to FMs, usually EMs. You can use this kind of shielding box. We have antenna, we have the satellite. Here, yes, distance is very short, but it's much better than doing the cables and other things, yes. And end-to-end mission test, you verify the base data flow of main missions. From command link, satellite missions, data downlink, and confirmation of data on a ground station PC. So ground station PC, radio, satellite radio PC, and if we did the camera missions, you check whether the camera really captured the image. Yes, that's important. And also, the camera has the image is really what you wanted. I mean that you may set up certain parameters, and the image was taken according to that parameter. So first you do this one, and make sure that yes, our mission is doable. I suppose I suggest you do this in if you can in a BBM phase before PDL. And when you build the EM, first thing you should do is a different. And the details you can add many commands, many parameters you can add, but after confirming this basic mission can be done, you can add a detail. And system function test, you move to FM assembly as soon as FM components delivered and start the function test as the integral system. You check the consistency of data sent from satellite. You may see that the hex data is sent, hex data appears on the computer screens, and you may think, yes, it's okay, but no. Convert hex data to real data. If the temperatures, you confirm the temperature you get is consistent with the satellite temperature. or if it is rotation speed, if it is really showing the rotation speed. And you should move to the environment test before all the problems, if there are some problems. And you can expect many problems. Actually, yes, you have many problems. So have enough schedule margin before moving to the environment test. And end-to-end long-term operations, yes. So it's good to find fixed bugs of flight software and operation rehearsals of critical mode, nominal mode, and the mission mode, and confirm the link budget. It's a compatibility with the ground station. So use the ground stations if the license allows. And deployment is, yes, 25% of university satellite ends up DOA. Many of them provide antenna deployment failures. So make sure antenna can be deployed in the worst case. And fit check. And CubeSat may not fit into the port at the satellite delivery. So the best, simplest way is to do the fit check with the official port from launch provider. You should do both for the EM and FM. And make sure they do the fit check before doing the vibration test. Okay. And do the fit check before and after. Yes. Okay. And operation phase. And in operations, obtain the frequency license as soon as possible. In Japan, we get only preliminary license before the launch. We need a full license to operate a satellite officially and publish a result. So we do the main mission first, achieve the mission success criteria as soon as possible. And to get the frequency license, we need to have two-way communications, uplink and downlink. And even if you have an anomaly, you should never give up. And PI should keep the motivation for the teams to follow the FDA. For the conclusion, well, CubeSat mission success rate is low, especially for the first satellite. Even for the second and third or fourth satellite, we failed. Actually, I failed my satellite even now. Yes. So there are many things. We can take a risk in CubeSat, but this doesn't mean the failure is accepted. So there are many lessons learned. Sharing the lessons and the root cause among the community is important. And Mission Assurance Handbook has been published, it's version 4. So I welcome your comments. I welcome your comments and to improve those Mission Assurance Handbook. Yes. And I told many times, external reviews, external advice is effective. Yes. So you can utilize this kind of KiboCUBE Academy. We have this KiboCUBE consulting sessions. And also at the QTech, in collaboration with JAXA, we have something called CubeSat Salon. This is a 1 hour free consultation service. It's open to overseas. You can check the internet and you can find a link. So it's available. And so I encourage us outside people. Yes. And then you can solve the problem very quickly. Yes. Don't hesitate to ask questions. Okay, now I can take a question. Yes.
Okay, thank you very much, Dr. Cho, for sharing your experience and very detailed and interesting lectures. So we definitely learned a lot. So before we move on to the Q&A sessions, so if you have any questions, please send your questions using the Q&A box. You can click the Q&A icon in the toolbar and you can send question to us. And again, when you write your questions, please state your name and affiliation. And the other announcement is to answer common questions received. So we will share the presentation slides and the recording of today's webinar later on the UNOOSA website. It may take some time for us to put up the recording data, but we will try to do it as soon as possible. So please visit our KiboCUBE Academy website later on. So let's move on to the Q&A session. So we are getting a lot of questions. Some of the individual questions have been answered separately in the Q&A box. So I pick up some of the related questions to today's lecture and start addressing them. So the first question to Dr. Cho is referring the two reports you mentioned that were done for JAXA in the first part of the lecture. They are available openly, even in Japanese?
Sorry, it doesn't question to me. Sorry, could you
The
say it?
two reports that you have done for JAXA.
Yeah.
Are they available
Yes.
to the public?
Yes, both are available. So Mission Assurance Handbook, English version is available, and check this one. For full difference, you can downlink. And another report, 439 page, yes, available. But unfortunately, it's a Japanese only. And you need to do ask ChatGPT or something to translate. Yeah.
Okay, thank you very much. So the next question is Jamal from Cyber Science Institute. Why the SLE protection was not verified after the design? It's a bit technical question.
Yes, I think it's a good technical. Well, main reasons we couldn't do the radiation test before the launch. Yes. Well, to verify this month, we need to simulate FEL. To simulate FELs, we need to have a radiation source. Yes, and then but the radiation testing facility is not easy to access, so we couldn't have a chance to do radiation test. But after that month, for the next satellite project, we did a radiation test. Yeah, and we verified 3-4.
Okay, thank you very much. So the next question.
Yeah, I've got two from Philip.
Okay, thank you.
Can you read it?
Okay. Which one?
Philip from Germany.
Okay. Philip from Germany. Thank you very much for sharing your insight. You stated that you studied these lessons learned during the pandemic based on the CubeSat project until 2020. Have you noticed any improvement with occurrence of root cause since you published the Mission Assurance Handbook?
Good questions. I think time is too short. We are promoting this mission assurance activities for the past 3 or 4 years. I think yes, we are shifting many university project. I think in the next year or two, I think we'll start to see the effect. Yes, it's about to coming up. Yes.
Osa-san, can you mute the someone in the panelist? Okay, thank you.
Yes, I did.
Okay, thank you. And okay, next question is okay. from anonymous attendee. So there is a high risk in terms of designing communication subsystem. What is your recommended system test to mitigate the failure? Do you have any suggestion for the key point to manage the COM design?
Well, I think you do the radio test. Use the communicate by radio air. That's one important. And use actual antenna. Actual antenna. So the important thing is use the flight models, because how you attach the antennas may depend on those workmanship. And so you really use the actual antenna, do the test by air, I mean the separated, and confirms link budget. So you modify power levels, and identifies how far you can communicate. And to identify, you really decode either by ground station or satellite side, whether you really succeed in sending the packet. So you confirm whether communication is successful or not by packet decoding. Okay, not by looking at a spectrum analyzer. You have to really, because you are doing the digital communication, after recovering digital data, it's success. So that's my recommendation. So recently, the satellite I supervise, we spent much time in that kind of test. Yes, they confirm really the link budget using actual flight model satellite. Yeah. So that's my recommendation. Yeah.
Thank you very much. The next question is from Ali Leines from El Salvador, PNC Awadi. I would like to know if there is a support system or a list of experts available for countries seeking external reviews of their missions, such as for MDR and PDR, etc.
Well, I think I told at the end, I think we have a KiboCUBE consulting sessions. And also, I say that I'm running a CubeSat salon in Japan, and it is available online. So you can ask, you can send the email. Yeah.
Okay, thank you very much. And the next question from Carlos Madron from Algeria. And based on your extensive experience in CubeSat development, what were the most critical and challenging risks you faced, and how are they mitigated? Additionally, if we classify risks into categories, design, development, launch, and orbital deployment, space environment, payload, and scientific objective management, which category would you consider to have the greatest impact on the overall success of our CubeSat mission? I want to know if there are any possibility to contact. Okay, sorry. The first part.
There are many aspects, there are many aspects. So, but you should, what I can say is that you should use a satellite bus, which is reliable enough. And so unless you have a very reliable satellite bus, you cannot do the mission. So if necessary, spend some money in the satellite bus and procure commercial product and test those commercial, because commercial ones, the quality of workmanship is better than students. Or students sometimes handwork very good, but sometimes very poor. And so how to assemble, how to make those by really handwork, it's really difficult to the quality controls. Company, at least they are doing some minimum kind of quality controls. So that ones we can still trust. But if you don't have money, you really need to be careful about how to assemble how to make those PCB, how to connect it, and everything. That one is really important. And also, most important, satellite must work as a system. So you try to do system test as much as possible. That's a one, yes. And as a system, it must work. Yes. That's probably the most important. Yes. And if yes, I think so. I stop here. Yes. So do the system test. That's all. Most
Thank you
important.
very much.
Yeah. And if there is a profile, contact me through the CubeSat forum. Yes.
Okay. So next question is from Enzo Gartobo. Do these lessons learned apply to innovative missions like software reconfigurable CubeSats or insert CubeSats?
Oh, sure, of course. It applies to any kinds of CubeSat missions. Yeah.
Great.
Even if you have some very sophisticated satellite, you still have to do all kinds of activities, the assured mission. Yeah.
Okay, thank you very much. And next question for okay, the next question from Jeremy Antonio Novus, Novus, and from University in Mexico for team extension and talent. What do you recommend to be the criteria for selection of team members besides knowledge for the missions to be successful? And how many people should it be in each country?
Well, I wouldn't recommend too many members. Well, sometimes I see the project having 100 students. Yes, it's not manageable. Yes, and well, I once the one project which was very successful was run by only by seven students. They made 3 satellites. Yes, it was quite successful. And another satellite project, I had maybe more than 40. Satellite was good. Satellite succeed, but management was a really nightmare. Yes, project manager did a very good job. So somewhere around that one. Yes, beyond 50, I think it's no, my opinion, it's not manageable. Yes, and so 10, 20. 10, 20, probably good numbers. Yes. And the most important one is the passion, passion and motivation, I think. But when at the time of satellite assembly integration testings, I think persons who really follow procedure, it's very important. Yes. Some students neglect procedure. That's not really good. Yes. So it's really the education process. Educate the students about the importance of following the procedure. Yeah.
Okay, thank you very much. Unfortunately, we ran out of the time. So let me see. So if you have questions, please send your question to the UNOOSA Access to Space at UN.org, and we will collect them and try to answer your question later on. So thank you very much, Dr. Cho. So really thank you for your very detailed and interesting presentation and for answering the question from the participant. And thank you to all the participants for your active participation. So as I mentioned, his presentation slide will be online soon on our website. And this webinar is recorded, and we'll try to put it up as soon as possible so that you can review the recordings later. And so again, if you have more questions coming later, please feel free to address them to this address, to UN address. And okay, and we would like to hear your feedback, so please answer the questionnaire form, and we will be sending your URL for the questionnaire form later. So with this, I'd like to thank everyone for engaging with us with many questions, and thank you very much, Dr. Cho, again. And we see you in another session of the KiboCUBE Academy. So thank you, everyone. Have a good day. Thank you very much. Bye.